Hello everyone, welcome to Chemistry with Professor John Nguyen. Today I'd like to take this opportunity to go over the chapter's gases, okay? and some practice exercises we have in the study guides here. All right, the key concept and skill for this chapter will be calculating volume, temperature, pressure, using one of those formulas, the gas laws. Remember, each gas law is represented by a formulas. All right, and then towards the end, we'll be calculating density, molar mass, and average speed, which is known as root mean square velocity of gas molecules. All right. First of all, we need to be able to get to the units that we want. For example, pressure. Usually we see pressure in inches of mercury, okay? And let's say we have to convert that into torr, ATM or kilopascal, we need to know how to do that, okay? Well, the first one here is shown for you. If you have 29.2 inches of mercury, 1 ATM, that's the normal pressure at sea level. That's 1 ATM equal to 29.92 inches. That's the conversion. So you set it up 1 ATM on the numerators on top over 29.92, cancel out the inches, you got the ATM. So that would be the answer for the second, for part B actually. And if you go on to the next conversion, 760 torr over 1 ATM, that will give you the answer for part A. So this calculation is good. Just one conversion will get you to ATM, and then second conversion will get to torr. So go ahead and put that in the calculator. You should get the answer. Okay. The and actually, I'm doing it right now with you guys too. Sorry, it's gonna take just a few seconds here. 29.2 divided by 29.92. So the answer for part B should be, if we keep it three significant figures, it would be 0.976 ATM. Again, everyone, 0.976 ATM for part B, just the first conversions. Now I'm going to go ahead and multiply that by 760, and that will give us, routed off to three significant figures, that will be 742. Everyone, 742, okay? 742 for this one. We good? Okay. Now, once you get the ATM, you still have to do for part C. When you get the ATM, then you can convert it to a kilopascal. 101.325 kilopascal over 1 ATM. That's going to be the last step, okay? And so if you do that correctly, you should get you should get 98.9 kilopascal for part C. Everyone, 98.9 kilopascal. All right, let's move on, okay? All right, so that's unit conversion for pressure. Now move on to the first gas law, which is the Boyle's law. Boyle's saw that if, as the pressure of, notice that if the pressure of a gas decreases, the volume of that gas increases. So they go opposite direction. If one increases, the other one decreases. Or if the pressure increases, the volume decreases. If you think about it, it makes sense. If you have a cylinder, if you compress, meaning you reduce the pressure, you reduce the volume, the pressure will increase. When you compress something, it's going to increase the pressure. okay, and vice versa. Uh, to put that in formula, boys multiply them together. P1 times V1, that's before, equal to P2 times V2, that's after, okay? So every time you change the pressure, you can calculate new volume. Or you change the volume, you can calculate new pressure. Okay, for example, a gas occupies 15.8 liter at 1.5 atm. Remember, they always go together. 15.8 times 1.5 times 15.8. Calculate its new volume at 4.5 atm. So you increase the pressure to 4.5. What would be the V2? So that's P1 times V1 equal to P2 times V2. If you divide both sides by 4.5, obviously, algebra trick, you solve for V2, and you should get 5.27 liters. It should be less volume because the pressure is increased. We are compressing the gas, so the volume should be less. Okay, so that's Boyle's law. You don't have to remember the name of the law as long as you know the formula. P1 times V1 equal to P2 times V2. Now, going on to the next one, Charles' law. Charles doesn't put pressure in the formula, only volume and temperature. And then of course he wondered what happened, if he changed the temperature. So it turns out they are directly proportional. Directly mean if one decreases, the other one also decreases. And if the one like temperature increases, the volume also increases. Makes sense. If you have a balloon or something, if it's in a hotter temperature, of course the volume will expand. Okay, so V1 over T1 equal to V2 over T2. And here's a good example. Carbon dioxide, 0.3 liters at 10 degrees Celsius. What's the volume when you triple the temperature Celsius? Now, when you triple Celsius temperature, doesn't mean the volume will be triple. Notice that the temperature has to be in Kelvin. So you have to convert Celsius to Kelvin by adding 273. Okay, V1 over T1, V2 over T2, solve for V2, and this is 303.15. You multiply both sides by 303.15. Denominator here is 283.15. So you do it carefully, you should get 0.321. So the volume does not go up that much. Okay, it's less than 10%. That's because of the Celsius. Celsius have to be converted to Kelvin. So the formulas only work for Kelvin temperature. Okay, notice that. And if you're calculating temperature, you're always going to get Kelvin, and then you can convert it back to Celsius if you need to. Okay, so that's Charles' law. And the third one is Gay-Lussac law. Gay-Lussac keep the volume constant. Just pay attention to the pressure and temperature. And yes, it turned out they're also directly proportional. P1 over T1 equal to P2 over T2. So if you increase one, the other one will increase as well. You increase P1 to P2, temperature also increases. Okay. Here's an example. Initially at 24 degrees Celsius, again, you have to convert that to Kelvin, at 360 kilopascal. Now, we don't really need the volume, but the problem gave it to us anyways. We're not going to need that for the calculations. Okay, it doesn't matter what volume, the calculation will come out, the same. But because of that volume, we got that pressure. Okay, 360 kilopascal over 24 degrees Celsius plus 273.15. We need to find what the later, the after we increases 50 degrees Celsius, also plus 273.15. What would be the new pressure? It's going to be higher, right? So do your math, multiply both sides by 50 plus 273, that should be 323.15. 323.15 multiplied by 360 divided by 24 plus that should be 297.15. You should get 390 or 391 kilopascal for P2. So that goes up. Let's go about a little bit less than 10%, 360 to 390, roughly about 390. Okay, now if you guys work on this one, this should be Charles' law. Yeah, by mistake I put it here, but this is actually a good example of Charles' law. And because the pressure stay the same, so you can safely cross it out. You don't need it, okay, because the pressure stay the same, 1.1 atm. So if you do V1 over T1 equal to V2 over T2, before and after, you should get V2 equal to 635 ml. Okay, now if you combine all those laws together, you will get what we call the combined gas law. P1 times V1 over T1 equal to P2 times V2 over T2. If you take away any of them, if you take away temperature, you get yourself Boyle's law. If you take away pressure, you get yourself Charles' law. If you take away volume, right here, if you take away volume, you get yourself Gay-Lussac law. So basically, combined gas law has everything you need, and that you can create Boyle's law, Charles' law, or Gay-Lussac law based on just the combined gas law. Okay, just taking 2 parameters at a time, not all 3, and not just pressure, volume, temperature. Just consider 2 at a time, and you get those laws. We got an example here when you see all 3 items in there: pressure, volume, and temperature. Notice that we converted to Kelvin, and then we need to calculate the volume after we change the pressure and change the temperature. So you do your math correctly, you should get 0.193 for V2. That's combined gas law. Now, Avogadro's law is very straightforward. It depends on the number of moles of a compound. Right here, if you get, let's say, 2.5 mole give us 56 liters. What if we got 4 moles? We add another 1.5 to become 4, directly proportional. Multiply both sides by 4, you should get 89.6 liters. Okay, now we're not talking about before or after. We're just going to talk about in general. How do we have a formula for that? It turns out, yes, we have a formula. P times V equal to N times R times T. This is the perfect gas law or ideal gas law. And in which P is the pressure, it has to be an ATM. So for this particular problem, we convert it to ATM. If you take 745 torque divided by 760, you got ATM. V is the volume. That needs to be in liters. Okay. N is the number of moles. If we got 655 gram, we can calculate molar mass, which is carbon plus 4 hydrogen, that's 16.05. Take 655 divided by 16.05, you get yourself number of moles, which is N. 25 degrees Celsius, we got to convert that to Kelvin, add 273.15, so you get about 298. All right, plug in the formula, PV equal nRT. If you take nRT divided by P, you get V. So you plug everything in you have, so you should get V right around 1019 liters. Now the ideal gas law is very useful. Not only we can use it to calculate volume, but we can also use it for calculating pressure, P is going to be N time R time T divided by V. And for this particular one, we got 2520 mole time R. R is a fixed numbers. It does have units too. Time 27 degrees Celsius, but we have to use Kelvin, so that's at 273.15, so we get about 300.15 divided by V, which is 180 liters right there. So you should get 345 ATM if you do it correctly. Now, if we have 4 moles of nitrogen gas at 35 degrees Celsius and 2.5 ATM, can we calculate volume? 4 mole. Yeah, volume is, remember PV equal nRT, so volume is P nRT divided by P. Here we go. N, we're given 4 moles. R, 0.08206, that's the fixed numbers. Temperature, we have to convert it to Kelvin, 308.15. Pressure is given. So if you got to plug everything in, you should get 40.5 liters. Now this number 4 is very interesting. It's an applications. With the ideal gas law, we can calculate N, which is P times V over R times T. Plug everything, you get everything in, you get 0.0039 mole. Now we are asked to calculate molar mass. By definition, molar mass is the mass divided by number of moles. So from this calculation, we got mole, and mass is given. So you take mass divided by number of mole, you should get molar mass. Notice that I convert pressure to ATM. That's required. I convert temperature to Kelvin. Okay, and before I plug in the formula for ideal gas law. Now after you're done, take the mass divided by the mole, we get molar mass, 72.1. If you do it correctly, it should be 72.1 gram per mole. All right, the rest of the calculations are very straightforward. I showed them all here. Just let me know if you guys have any questions. And a couple more examples for density calculation. We got the formula for density here. It's all based on ideal gas law. And assuming, in this case, we assume 1 mole. And a couple of examples, calculating the density. And finally, calculate the root mean square velocity, which is the average speed of a gas. And very important that the molar mass has to be converted to kilogram, which is divided by 1,000. Okay, there, divided by 1,000. Molar mass of nitrogen is 28, but divided by 1,000, that's why it's 10 to minus 3. All right, real gas laws is great. That's what reality. Gas molecules interact with each other. They do take up space, so that's why we have to make the correction for the interaction. That's the intermolecular force, and we have to make the correction for the volumes of the gas molecules. This calculation will not be on the test, but it's absolutely good to know. Okay. On the next page of the study guide, show all the constants A and B for each gas. So it's a lot of work, but it's definitely doable. All right, thank you everyone. See you in the next video.